In the last video, I set up a related rates problem. I was talking about a ladder that's sliding down a wall. And there are two things that are changing as that's happening. There's the distance from the top of the ladder to the ground, and there's the distance from the bottom of the ladder to the wall. Both of those things are changing as the ladder is moving in free fall. But the ladder is staying the same height as it's doing that. So we've got a connection between those two changing values. And because of that, we can solve the related rates problem of talking about how quickly one of them is changing with respect to time based on the derivative of the other with respect to time. I've put together a little reference sheet for how you solve related rates problems that can be helpful in just giving us a process for working through these problems. All right, so the first thing we want to do is we want to make a drawing of the problem. And then we're going to make a list of all of the facts that we know. And we're going to keep track of both the static values and the rates. So how quickly the things are changing. And we'll also be interested in one specific moment in time. So we will think about the static values that are happening at that moment in time. We also want to think about the thing we're being asked to calculate, which is probably the rate that we don't know. So we're given the rate of one or more of the things that are changing, and we're asked to find the rate for the missing factor. So we should create variables to express those values, and we want to express it in that math notation. And we're going to use derivative notation for the rates. We're talking about how quickly something is changing over time. And then step 4 is that we want to come up with some way of relating all of the variables we have. And it's going to be some definition of something, maybe a formula or an identity. There's just going to be some way of tying all of the facts together in a mathematical statement. Then we can use implicit differentiation to differentiate that formula with respect to time, because we're interested in time changing over the course of this story. And then we're going to substitute in all the missing values we know and solve for the missing piece. So let's go back to the problem that we started with in the last video. We've got this ladder sliding down the wall, and we used X to talk about the distance from the foot of the ladder to the wall, and we used H to talk about the distance from the top of the ladder to the floor. Now remember that H and X are not really specific values so much as they're functions of time. And so when we say that the base of the ladder is moving away from the wall at a constant rate of 1 foot per second, what we're saying is that the derivative of our X value with respect to time is going up by 1. All right, because this variable is increasing by 1 foot per second. And we want to know how fast is the top of the ladder sliding down the wall. So we want to know what's dH dt. So H is our height. How is that changing over respect from time at the specific moment when the bottom is 8 feet away from the wall? And so that is steps 1, 2, and 3. And step 4 is coming up with, since we've got X and H are our two factors that are changing, we want to find some way of relating those two factors. And what we realized was, since this is always going to be a right triangle because the wall and the floor are always forming a right angle no matter what the ladder is doing, we can use the Pythagorean theorem to say that at any moment in time, h of t squared plus x of t squared is equal to 10 squared. And really, we're just going to go ahead and call that h squared plus x squared is equal to 10 squared. This is a little bit sloppy, but we're just going to remember that sometimes X is going to be a specific number and sometimes X is going to be a function of time. And so we'll just do our best to make sure we keep track of when that is. All right. Step 5 is, now that we've got this relation between our two factors, we're going to implicitly differentiate that with respect to time. So you'll notice that t is not one of the values in this formula at all, but that's okay. We can still implicitly differentiate. So the derivative of h squared with respect to time is 2h times dh dt. Notice that when you're differentiating with time, you're always going to include this something over dt. And the derivative of x squared with respect to t is going to be the same. It's going to be 2x dx dt. And on the other side of the equation, what's the derivative of 10 squared? Well, 10 squared, or 100, that's just a constant. So the derivative is going to be equal to 0. So now we've got this relationship, which has dx dt in it, and it's got dh dt in it, which is what we want to solve for. So we want to solve for this expression given all of these extra factors. All right, so we can substitute. We want to think about this at the precise moment that the bottom is 8 feet away from the wall. So the bottom is x, so we want to substitute 8 in for x. 2 times 8 times dx dt, which is 1. And over here, we've got 2 times h. So what is h equal to? So this is part of the hint for step 6 of our problems. You may need to calculate some missing values from the original formula or by some other process. So at the specific moment that x is equal to 8, can we figure out what h is equal to at that specific moment? Once again, we can use the Pythagorean theorem. So we can solve for h because h squared plus 8 squared is equal to 10 squared. All right, so h squared plus 64 is equal to 100. Subtract 64 from both sides, you get h squared is equal to 36. Take the positive square root because h is definitely a positive number, and h has got to be equal to 6. So substitute h in for here. We've got 2 times 6 times dh dt. And now that's equal to 0. So we've substituted all of the values we can come up with into this equation, and now we can solve for dh dt. So we've got 12 dh dt plus 2 times 8 times 1 is 16 is equal to 0. 12 times dh dt is equal to negative 16. Divide both sides by 12. And so we have dh dt is equal to negative 16 over 12, which is equal to negative 4 over 3. All right, so first question is, this is a real world problem. Does it make sense that our derivative is negative? What does a negative derivative mean? A negative derivative means that over time, h is getting smaller. H is going down over time. Does that make sense based on this problem? Well, yeah, it does. So as the ladder is sliding away from the wall, the top of the ladder is going down towards the floor. So h is decreasing, and it's decreasing by 4/3. What do you think the units for this problem are based on what we have here? Well, our distances are in terms of feet, and our time is in terms of seconds. So what we can say is that dh dt, we can say the top of the ladder is approaching the floor at 4/3 feet per second at that moment. This is only true at the specific moment that the base of the ladder is 8 feet away from the wall. Okay, so that gives you a sense of how to solve a related rates problem. It's that 6-step process. I'm going to have that linked in Schoology, so you can print that out and be sure to use that every time you attack a related rates problem. It just really takes a complicated problem and figures out how to turn it into something that you can track pretty easily just by going step by step.